Okay. So good afternoon to everybody. Welcome to this new seminar of the MOX Colloquia. And today is a pleasure to have with us Volker Mehrmann. I would like just to spend some minutes to introduce him. And there are a lot of news and things to do, but so sorry, Volker, if I selected just the most important one. So Volker received his PhD from University of Bielefeld in Germany, and then he spent the 80s in USA at Wisconsin and Kent State, and then in Germany at TBM Research Center in Heidelberg. Then he became full professor in '93 at TU Chemnitz, and then from 2000 at TU Berlin, where he's now. He's member of the European Academy of Science, and he was also president of GAM, the International Association of Applied Mathematics and Mechanics, also chair of Matheon and of the Einstein Center in Berlin. And since January 2019, he is president of EMS, so the European Mathematical Society. He's also Science Fellow, and he held an ERC Advanced Grant. And moreover, he was also member of the year's mathematical panel. He's editor of several journals in numerical analysis and editor-in-chief of the journal Linear Algebra and its Application. And his research he has a lot of research interest. I would like just to mention, of course, numerical analysis and scientific computing, applied linear algebra, control theory, and the solution of differential algebraic equation, and recently also on energy-based mathematical modeling. And with this respect, today the talk of by Volker is about energy-based modeling, simulation, and control applied to real-world digital twins. Please, Volker, the virtual floor is yours. And Volker ask if you have some urgent question, you can write them by chat, so he will be happy to interrupt his seminar. Otherwise, we can have standard questions at the end of the talk. Thanks, Volker.
Yeah, Christian, thanks a lot. And thanks a lot for the invitation to give a lecture here. Yeah, I would like to talk about my recent hobby. I mean, actually not only a hobby, but it's really on my soul in recent years, and that's energy-based modeling, simulation, and control. And so let me start with some theses. So most modern key technologies in industry, and I really put the emphasis here in industry, require modeling, simulation, and optimization of dynamical systems. And most real-world systems are multi-physics systems, combining components from different domains and with different accuracies and scales. You know that very well in MOX. Modeling also becomes more and more automatized, linking subsystems of numerical methods in a network fashion. And we also have now large sets of real-time data available that should be used in modeling and model assimilation. In all of this, we need to quantify the errors and the uncertainties. And in the future, we will have digital twins of almost every process or product. And so that means we will have to adapt the models and also the methods during the lifetime of a product or a process. And also, I think that modeling, analysis, numerics, control, and optimization and data science techniques need to go hand in hand. And if you really want to do optimization and control and data assimilation effectively, that also requires model reduction. And so all these items I will speak about. So first of all, let me tell you my definition of a digital twin. There are many definitions out there, but a digital twin for me is a hierarchy or a catalog of models, dynamical models of real physical systems. These are mathematical equations, but with inputs and states and outputs and parameters that allow at the same time simulation, optimization, process control, prediction. And they also include data-driven models that have sensor data and measurements and allow them to monitor, incorporate this information about the current state. And digital twins are and will be used for data analytics, prediction, risk and uncertainty analysis. And it also may employ modern techniques of learning or data assimilation to improve the model equation. And the main point I want to make is a digital twin is not a static virtual model. It changes in an evolutionary way when improvements are necessary or possible. And what are the major aspects, to my opinion, of digital twin from the mathematical side? I think it needs a system and network theoretic approach, and software has to be generated automatically via modeling languages. And as I will tell you, energy-based models are key to this. Also, for every part of the twin, we not only need one model, we need a whole hierarchy or catalog, from very fine for simulation to reduced order for optimization and control. And we should be able to switch between the models in the discretization in space and time. That we should be able to quantify uncertainties and have a coupling between the simulation and optimization tools. And a major aspect that is coming when you go to industrial applications is sharing of computing resources. So some things will be done on the edge of the computer and some will be done in cloud computing, and the model should be evolve with time. So what can we do to make the digital twin reality? And I'm working on several digital twin networks, but let me give you one, which is gas transport. This has to do with the energy change in Germany, and that we will all face in the climate change, that we would like to have a digital twin of a gas network. This could be natural gas, or this could be hydrogen in the future, but the same procedures apply in other type of networks. So if you have such a gas network, there's a lot of mathematics going in there, and to build a digital twin, we have a so-called collaborative research center, Transregio, together with several universities, and we have data from industry. So what are the components of a real gas flow model? So it's a large network of partial differential equations with constraints. So typically one uses Euler's equations, including temperature, to describe the flow in the pipes. You have a network model. You have flow balance equations, so Kirchhoff's laws at the nodes of the networks. But then you have also many other network elements, pipes, valves, compressors. There's also controllers, coolers, and heaters. And you also have surrogate models. So, for example, the picture that I show here is a compressor station. So there's a huge building, and it does not do much more than the pressure and the velocity of the gas that is coming in is changed so that it comes out with a higher pressure and different velocity. And essentially, it's a control system which follows the curve. And that is mainly based on data because it's almost impossible to model this whole factory. And the other problem that we face in real gas flow models is erratic demand and nomination of transport capacity. Erratic, why? Well, there is weather, which changes the demand, there is speculation on the energy stock market, and there's also politics involved. We hear that every day, that the guy from Belarus wants to switch off the gas pipelines and things like that. So there's a lot of erratic and stochasticity in the models. And in the future, and that's a big project currently going on in Germany, is to use the gas network as energy storage for hydrogen that is, or methane that is produced from unused renewable energy. So you see, there's a lot of difficulties involved. So what is on top of it, it's a huge network. So these are the big lines in Germany. And if you look at such a node here, then it's again a big network. And each of the nodes in that is again a big network. And each of the nodes in that is again a big network. So it's a huge hierarchy of networks that play together. And it apparently goes from every household that is using gas to the producers of gas in Russia or Norway. So how can we deal with such a complicated system? So what we would need is, for the digital twin, is a model hierarchy. So let's start with the top model. The top model in this description would be the compressible 1D Euler equations. Now you could ask, why the 1D? Why not 3D? Yes, actually, if you wanted to mix hydrogen and natural gas, you would have to do the 3D Euler equation. But let me start with the 1D Euler equation in a pipe flow. That's a reasonable assumption. Although I must say, the higher level of 3D would be natural to go. So we have mass conservation. A rho is the density. Kw is the heat transfer coefficient, and we have a temperature T, wall temperature Tw, velocity V, gravitational force G, pressure P, friction coefficient lambda, the height of the pipe H, the diameter of the pipe capital D, the internal energy, and R is a real gas constant. So we have mass conservation, we have momentum balance, and we have energy balance. And actually, you should also have an entropy balance equation, but I didn't write this down here. So this is a partial differential equation. And as is usual, when we go to this, we look at it, maybe we can simplify the model. And so what has been done also in this research project has been done to build a whole model hierarchy. On top of this, there are the Euler equations. Then you have one simplification. You say that the temperature is constant. Then you have the isothermal Euler equations. You could say that the derivative of rho v squared, this is this term here, and that this term is small. Then we get the so-called semi-linear model. You could also say that the time derivative of rho times v is small. Then you gets the so-called friction-dominated model. You could go to the stationary version. So you say everything where there's a time derivative is 0. Then you get the so-called isothermal algebraic model. And actually, we're working together with discrete optimizers. And for them, even this isothermal algebraic model is too complicated. So they replace this by a piecewise linear approximation. So every element, node, or edge in the network is modeled via such a model hierarchy. And for each of them, you could also have a reduced model, a surrogate model, or a data-based model. And if you do that, that allows you to do adaptivity in space, time, and model via error estimates. If you want to have an overview over this, there's a recent preprint in English. There was an earlier version in German about this. This is the current version, which describes every component in this model, and it has also can serve as a benchmark example. So let me give you this in a little bit more detail. So the full model would be the isothermal Euler equation consisting of continuity and momentum equation, together with the equation of state for the real gas. Then we simplify this equation by assuming the pipe to be horizontal, so and the speed of sound to be constant. Then we get this nonlinear model. And if the gas velocity is much smaller than the speed of sound, which is typically the case, gas is the speed of a bike, then we can neglect the nonlinear term in the spatial derivative. That's model M2, and the stationary one would be model M3. And then what we have done is, and it's rather nasty work, we've computed all the sensitivities for every change from one model level to the next. And also when we do changes in the time and space discretization. And this we have used to adaptively change the model, the space and time discretization. Here's a test network, very simple one. That's one of our playgrounds that we use. So there's a source term here, there's a compressor station here, and there's a compressor station here. And so you take such a model. It doesn't really matter at the moment what the different components are. And with the compressor station, you can trigger increase the pressure in a component. And with all these components, we build a model, and then we ran it through this model hierarchy and with space and time discretization. So we formed the cost function. This is the modeling error. This is the space discretization error. That's the time discretization error. And JP is the number of pipelines that we have in the model. And we drove this smaller than a tolerance, and typically that led to reduction in computing time by 80%. And then we also added this into the optimizer. So the optimizer for compressor cost. So here D is a discretization error, eta is a modeling error, eta M is a modeling error, and eta is a total error. And in this way, you can make sure that every optimization step, you get a feasible model, and you play with the different tolerances and the different sizes in order to drive your model. And for example, this is a network with 40, and this is a network with 135 pipes. And these are industrial networks. And you can show that the modeling error is relatively easy to control. Once you're here, you're done, and then the rest is done by the space and time discretization error. So this just gives you an indicator that we can use that. So let me immediately evaluate what we have done in this before I come to the energy-based approach. So we have created model hierarchies of detailed and simplified models. We can use space, time, and model adaptivity to speed up simulation time and to control the behavior of optimization methods. It's very successful in this gas network. And we have similar approaches for district heating and power networks. But what if we want to combine different networks together? And this is currently a hot topic, combining power and gas, and power and heating works together. So what can we do there? So as mathematicians, we could make a wish list. We could make a wish list. What do we need for digital twin models? Well, This is the dream here. Want representations so that you can couple models across different scales and physical domains. We want a representation that is close to the real physics for open and closed systems, so control and simulation. And as a mathematician, you want to have nice algebraic, geometric, and analytical properties. We would like to analyze the model's existence, uniqueness, robustness, stability, uncertainty, errors. If it's nonlinear, and also if it's linear, one would like to have a normal form, local normal forms that describe the system behavior. It should be good for space and time discretization and model reduction. And it should be good for simulation, control, and optimization. And in German, we have an animal. This is called the egg-laying wool milk saw. In English, it's called the jack of all trades. And so is there a chance that we have something like this? And the idea to get something like this is based on energy-based modeling. So what is behind that? This is not, it's about 20 years old, this idea. It comes out of the control community. And so the idea is to use energy or power as a common quantity of different physical systems that are connected as a network via energy transfer. You split all the components into energy storage, energy dissipation components, control inputs and control outputs, as well as interconnections. And you use a so-called Dirac structure, and I will tell you what that is a little bit later. It's a geometric structure to combine the submodels. And we allow every submodel to be a model hierarchy, as I requested. And the system theoretic way to realize this are so-called dissipative port Hamiltonian systems. And that was started around 2000. If you want to have a nice lecture notes that allows you to do this in a course, is by Arjan van der Schaft and Dirk Jelsema. It's an open lecture notes that you could use, which shows this very nicely. So what is a port Hamiltonian system or dissipative port Hamiltonian system? I will describe it to you first on the level of just ordinary differential equations. So you have a differential equation x dot equals j minus r times the gradient of a Hamiltonian. So J is a skew-symmetric or skew-Hermitian term that describes the energy flux among storage elements, energy storage elements. Then the Hamiltonian describes the distribution of internal energy among the energy storage elements. R is a symmetric positive semi-definite term which describes energy dissipation or loss in the system. And then we have a factor B minus P here in front of the input, and we have an output, and the output has a B plus P here, and then you may have a feed-through term. If these are operators, then you are in the infinite dimensional case, and then you look at appropriate function spaces. But let's stay for the moment with the ODE setting. Why should this be a good approach? So first of all, port Hamiltonian systems generalize Hamiltonian systems that we all know from physics, and also gradient flow systems from thermodynamics. The conservation of energy is replaced by the dissipation inequality. So instead of conservation of energy, now you have that the Hamiltonian at time t1 minus the Hamiltonian at time t0 is bounded by the integral from t0 to t times this quantity, which is the inner product of the output with the input. So they have to have the same dimension. And this is the provided energy to the system. Provided means also could be also taken out. So this is the idea to stay close to physics. Then the second property, which is very important, is if you take two port Hamiltonian systems and combine them in a power-conserving interconnection, then you again get a port Hamiltonian system. So that allows you to do modularized network-based modeling. Then typically this Hamiltonian is a Lyapunov function, so port Hamiltonian systems are stable and passive. That means they don't generate energy by themselves. And the port Hamiltonian structure allows to preserve physical properties in Galerkin projection and model reduction, and they are nice algebraic and geometric properties, and they're easily extendable. So because of these importance, what has been done is they have been looked at in all kinds of physical domains: electrical power, district heating, water networks, electrical circuits, poroelastic networks, mechanical systems, magnetohydrodynamics, thermodynamics and reactive flow, chemical engineering, and I could mention many more. But in our gas networks, we also have algebraic constraints like Kirchhoff's laws, position constraints, conservation laws. So we would like to add algebraic equations. And that has been on my agenda for the last 5 years, I would say. There are many different ways that one can go, in particular if you want to go partial differential equations. But let me again stay first for the moment with the ordinary case. And so 2 years ago, with my PhD student Ricardo Morandin, we introduced the following definition. So this is a complicated slide, but let me go through it in detail. So we have a state space. Typically here in the finite dimensional case is a subspace of Rn. Then we have a time interval, and we look at the extended state space, which is a Cartesian product of I and X. Then we have now in front of the derivative, we have a matrix function here, which could be singular. That encodes the algebraic equations. And we have a term, vector term R of t and x here. And we have a vector term E of t and x here. This E is the so-called effort function, and this R is the so-called time flow function. So that looks very complicated, but if you think for the moment that E is the identity, and capital E is the identity, and E is the gradient of the Hamiltonian, then this is the only extra term that we have here, and this one, I will show you why we need that. Okay, so you write down a system in this way, and then we call this port Hamiltonian differential algebraic equation if you have two structure properties. So first of all, you have JB minus B transpose N is skew. That's easy. It essentially means that J is skew. This skewness is given, and this is just a skew symmetric part. So that is easy. But then you have this matrix built from the dissipation matrix R, the P transpose, and the symmetric part of the feed-through term, that this has to be semi-definite. And then you have two conditions which relate the derivatives of the Hamiltonian to the rest of the equation. So the space derivative, or the gradient of the Hamiltonian, is E transpose times little e. So if E would be the gradient of the Hamiltonian, as we had it before, and E is the identity, then this is just the gradient of the Hamiltonian, is the gradient of the Hamiltonian. But with the E here, we get that restricted. And this term here is the time derivative that is related to relationship between this E here and this R. So why did we need such a complicated definition? The first thing is we have a dissipation inequality. So if you have such a system as described on the page before, and you put the effort function and the input together, then the total time derivative of the Hamiltonian is given by EU transpose W EU. Now W was positive semi-definite, so this term here is negative. And plus Y transpose U, and if you integrate that, you get the dissipation inequality. So you get the same, even though you've generalized this much more, you get the same. And why did we have to go to such a complicated model? This is because we would like to have transformation invariance. So we would like to be able to go to a different coordinate system or change of variables. So if you have any local diffeomorphism, so x is phi of t and x tilde, differentiable from this state space to x is a local diffeomorphism, and U is a pointwise invertible matrix, then you can form this transformed system where the E tilde is U transpose times the composition of E and this phi function times the inner derivative. That's the new E tilde. You have a new skew symmetric term, you have a new dissipation term, and this is again a Port Hamiltonian DAE. And to every solution x tilde u and y, there corresponds a solution x u of y of the original DAE, where x is just phi of t and x tilde. And if this diffeomorphism is global, then the two systems are equivalent in the sense that they have one-to-one solution sets. So, and without these extra terms, this R tilde and this E tilde here, we would not get transformation invariance. So that is a very important result here, that you can do changes of variable in your Port Hamiltonian systems in a global or local way, and you get a system of the same structure. And then the second thing why we needed to go to this more general framework is that we want to get a Dirac structure. So let me explain to you what a Dirac structure is. So you take a linear space, F or manifold, and you take E to be its dual space. So E is a set of efforts and F is a set of flows, and you define a bilinear form on the Cartesian product by taking E1 inner product with F2 and E2 inner product with F1, where this is a duality pairing. Then a Dirac structure is a linear subspace D of this Cartesian product that is orthogonal to itself in this bilinear form. And these F and E's are called flow and effort, as I mentioned already. And in finite dimension, one only needs to prove that this subspace, linear subspace, has the same dimension as F, and that E intersection F is 0. And in the differential geometric viewpoint, you talk about a modulated Dirac structure over a subbundle of the tangent space, the Whitney sum of the tangent space, which is dual cotangent bundles. And then it's a Dirac structure if locally it's a linear Dirac structure. So that's a differential geometric description. And if we have such a Port Hamiltonian DAE, we can make it autonomous. I haven't said that so far, but we can always make it autonomous. And then you can split the space or the manifold into the part corresponding to ports, storage, and dissipation terms. Also, we participate the flow and this E function in these three parts. They sit in space and dual space. And then we define a subbundle in such a way, F plus, and there's this gamma matrix that we had before together with identity and minus identity times E is equal to 0. And this alone in this structure with the skew symmetry of that gives you that we have a Dirac structure. So there is a direct mapping of what we have in the system equations written as an ordinary differential equation or the differential algebraic equation to the differential geometric structure. And there's also a Lagrangian framework here in the background, which I will not discuss here. So in the last years, we have done a lot of work in this direction. So for example, we've looked at structure preserving time discretization so that the time discrete system has a dissipation inequality and the power balance equation, and it has a discretized Dirac structure. And it turns out that Gauss-Legendre collocation or partitioned implicit Runge-Kutta methods do the job. And that's really nice because that means we have a class of time discretization method that we can directly apply. We have also looked at control design, and actually using this diffeomorphism framework, we can use the non-uniqueness in the representation to obtain robust representations under perturbations. We have looked at local and global normal forms, and we've done perturbation analysis. And we have also looked at different PDE formulation, and will be my next topic. So we would like to apply this to the Euler equations and to our model reduction there. And in order to do this, we have to go to the PDE version. And there are many different versions how to extend it. You could go linear operators way, you could look at structured PDEs, or you could go to a direct generalization of what I've just shown you for differential algebraic equations. And let me explain to you on the basis of these gas transport. So 1D, and I take an interval, time interval AB, space interval AB and the time interval T. And I choose a state space, a linear subspace of a vector space product of two spaces, ZD and ZB, where ZD is a vector space of functions from this interval I to R and D, and that B is is equivalent to some Rn and B. So D stands for densities and B stands for boundaries. And then this is your state space, and with this you also construct a flow space and an effort space, as well as an input space and an output space. And then you introduce a duality pairing between these inputs, these efforts and flows. It's just the inner product plus the boundary inner product. And the same thing for the inputs and outputs. It's the inner product that we had before plus what comes from the boundaries. And the boundary incorporation was the most difficult part in this modeling. And it's very often ignored in Port-Hamiltonian PDE models. The boundaries are considered to be homogeneous, and that makes it a little bit difficult. We use the usual definition of skew symmetric operator, symmetric operator, positive semi-definite operator, and positive definite operator, and the transpose of an operator. So it's essentially it's the same as in the matrix case. And then we can formulate Port-Hamiltonian operator DAEs. This is done here for the autonomous case, and we don't have a feed-through term, and that also implies that we don't have this P value, so the equations look a little bit easier. So Z is the state, U is the input, and Y is the output. And we have a Hamilton function. So E here is a storage flow operator, and it can be viewed as the Hessian of the Hamiltonian. J and R are again structure and dissipation operators. G is support. And they are all maps from linear spaces from the tangent space of Z to the flow space, from the effort space to the flow space, from the input space to the flow space. And E is the effort function, and H is a Hamiltonian density function. And the system is port Hamiltonian if we have the same thing as in the finite dimensional case, that J is skew, R is symmetric and semi-definite, and the flow and effort functions are related by the same notation that we had before, that the Frechet derivative in this case of the Hamiltonian with respect to the state is given by E transpose times capital E times little e. We don't need the second term because we have an autonomous system. And that immediately gives us such a relationship between the derivative of the Hamiltonian with respect to Z multiplied by the density and the boundary of function W, that can be written as E of Z transpose E of Z times W for all Z and W in the tangent space of Z. And now I will describe the difficulty that is coming in. We often have that we have non-homogeneous boundary conditions, and then we have to incorporate them into the port Hamiltonian system. And this we do by introducing so-called boundary skew symmetric operators. So we have a port Hamiltonian, B port Hamiltonian system if we incorporate the boundary conditions with extra operators into the system. So the boundary operator is UB is U times E, and the output YB is Y times E. So you add these two algebraic conditions to the system, extend your system, and then we get a port Hamiltonian descriptor systems in the same way as we had it before. So this is a little bit more complicated, but we can do that. And for the gas flow, we had this set of compressible 1D Euler equations, same slide as before. And so you define state variables, density, velocity and temperature, write the equations in this form, express T wall temperature minus temperature as delta T, and then we get such a port Hamiltonian system. E of Z is J times X of Z E plus G of delta T. And the J matrix operator is this operator which is skew symmetric. And it, at first sight, it doesn't look skew symmetric because we have the same term here, but note this is a derivative, so the first derivative, so we get a minus sign when you go to the adjoint. So that's why this is the same, and it's a B skew symmetric operator, and because E transpose JZ is just what is happening on the boundary at 0 and the endpoint of an integral, and then the Hamiltonian is what you had before, but it satisfies this extra condition that EZ is E, so this extra condition. And so with these extra boundary conditions, we get a system which looks like this, and then we add these boundary terms to the system, and then we get a port Hamiltonian descriptor systems as in the previous case. And the boundary operators are given by the mass flow at the beginning and this E plus rho at the endpoints, the two endpoints. And this you can use for interconnecting Gauss networks using conservation of momentum. And this extra equation U E times UB is can be used for boundary conditions. So, and we get this Hamiltonian condition. So this is the part, the usual part, and this is the part coming from the boundary conditions. So we can frame our gas network in this way. And all the submodels here in our model hierarchy, we framed as B-port Hamiltonian systems. The only ones that are a bit strange are the ones here, these nonlinear models, because they are not really physical. We can write them port Hamiltonian, but not in a physically good way. Okay, so it would be too complicated and too technical to give you all the examples, but every single one in here has been reformulated. And now let me come to the last part. We want to do model reduction, because if we want to do optimization or control, we need reduced models. So the first thing that is a nice observation is if you have such a port Hamiltonian system and you do a Galerkin projection, so X is replaced by BR, XR, either from infinite to finite or from finite to small, then the projected system by Galerkin projection is again a port Hamiltonian system, and all the properties are preserved. So that's a fantastic result, because it allows us to do discretization in space and discretization in time and model reduction in the same way. Let me mention that you can do that with different ways. You could use tangential interpolation, or you could use moment matching or reduced basis method. Whenever you have a Galerkin approach, you can do that with a port Hamiltonian system. And let me describe it with tangential interpolation. What is that? So you want to replace it by a reduced model that is a good approximation to y over a wide range of inputs. You do this by looking at the transfer function. So this is a linear approach. You take interpolation points, sigma and mu, and interpolation directions k and l. And then you construct a transfer function of the reduced model such that it satisfies these interpolation conditions. At the interpolation points multiplied by the direction, the two functions are the same from the left. And these interpolation conditions can be enforced by Petrov-Galerkin projection, which you construct from Krylov subspaces. So you look at Krylov subspaces, you start with a different tangential directions, you multiply with the input matrix, you solve a linear system with this matrix here, and you do this also from the right, and then you project. So that's tangential interpolation. But the reduced quant, if you do Petrov-Galerkin, different one from the left and the right, you usually give up the port Hamiltonian structure. So that's why you use Galerkin, but that usually means that the right interpolation conditions are the only ones, the other ones. Now, if we have a DAE, the unfortunate problem is that the polynomial parts of the transfer function is not matching. The algebraic equations are not properly reflected, and there you need to do some extra work. And here's an example where we can do that. It's a structured situation. So we have a semi-explicit system. E11 is invertible and J22 minus R22 is invertible. And in this structure, you can prove that if you construct a Galerkin projection and you fix the feed-through term by a slight modification, then the reduced model matches the polynomial part and it does tangential interpolation. And so it's a port Hamiltonian DAE if the projected W matrix is positive semi-definite. And in many cases, this can be achieved, for example, if we don't have a feed-through term. And let me finish with showing you an example for the gas transport model. So here's a network. We have edges and vertices. And on every edge, we describe conservation of mass and balance of momentum. This is for the propagation of pressure waves on the acoustic timescale in such a gas network. It's the second level model, the ones which are not so physically interpreted. You have a transport equation, and you encode the physical properties of the flow and the fluid and the pipe in these coefficients, and the damping in this dE. So P is the pressure and Q is the mass flux. Then you write down Kirchhoff's laws, so conservation of mass and momentum at any vertex of the system. And then you add inputs and outputs. As output, use the mass flux in and out of the network with the exterior vertices. And as inputs, use just the pressure. Then you have to set initial conditions, and we get a quadratic Hamiltonian, and that we use for Wallachian projection. So this is, you can do on the PDE level, you can do on the discrete level. If you discretize it with a mixed finite element space discretization, then you get a large scale system PDAE, and here the Q is not there. This you can scratch here, so it looks like exactly like the systems that we had before. Mass flux and pressure, the damping term, and the Hamiltonian is only in the first two variables. The last variable here, the X3, is corresponding to the Lagrange multipliers for the constraints. And we have an input term here in the middle equation. This is the Hamiltonian. And you can analyze convergence, error estimate, stability, and everything for that. And this is what you get when you do curve subspace projected model order reduction. So what you see here is blue is a discretized model, and red is a reduced model. So that started with 10,000 degrees of freedom. The reduced model here with 5 modes. You cannot already see the difference. A slide at the corners here, you see a little bit of a difference. If you go to 10 modes, you cannot see any difference. And the more damping you put into the game, the better it is already on the level. So this shows as a clear picture that this Port-Hamiltonian structure together with model reduction works extremely well. So I could talk for about 3 more hours about all this, but let me conclude now. What about our wish list? So we had all these nice requirements, and the Port-Hamiltonian PDAE or partial differential ideal, almost all the wishes are fulfilled. So I think they are an ideal class, but there are many things to do: real-time control, optimization, other physical domains. We don't know how to put stochastics into models yet. We have worked on stability analysis, would be internally different talks, and error estimates. There's also very nice results on preconditioning and on data-based realizations. There's an open problem here. Software would be very good. And at the moment, we have a huge research projects together with the Siemens company on doing digital twins for turbines and additive manufacturing processes where we use exactly that approach. So with this, I would like to conclude and thank you very much for your attention and my sponsors for their support. And more details you can get on my website. Thank you very much.
Thanks, Volker, for this very, very interesting and inspiring talk. And I would like to, I didn't see any question by chat, so we can start the discussion. Please, you can raise your hand or take the microphone directly if you prefer. I can start with a question for Volker. general, let's say, question. You mentioned that at slide 43 or 44 that this method of energy-based modeling, okay, is yes, this one is let's say very general in some sense, okay, but which is the main topic or the requirement the model should have, in the sense that you have applied for your gas flow model. My question is, anytime you have a hierarchy of models or fractal, let's say, models that are repeated under different scale, you can apply this, or maybe this is more general?
For the digital twin, yeah.
Yes, just to understand which is the
so that
other context.
Yeah, there are two aspects in this. The hierarchy you need for the digital twin, so that you can steer the accuracy and the speed in a better way. The port Hamiltonian you need for the coupling. So if you really want to build a network of models where different components come together and you want to do it in a efficient way, I would say efficient in the sense that you don't have to do everything by hand, then the port Hamiltonian approach is really ideal because you can do model coupling in a simple way. But that means you have to identify the inputs and outputs, and we have to do this in such a way that it is really going along with the physics. Otherwise, I think you have to do it by hand every time you couple different model classes. And the energy helps because energy is universal.
Sorry, because the energy?
Yeah, energy is universal.
Okay, universal.
And so that's why, for example, if you couple a structural mechanics model to an electrical model, usually the electrical model will not be seen by the mechanical model because they live on different scales. But if you do it via energy, then you see them.
I understand. And this is independent of the dimension. You can apply also to 3D.
You can apply to 3D, but what you have to do is in general is you have to go back to the physics. One thing we noticed, I didn't talk about this here. For example, we looked at polar elasticity, and there we noticed that in the period between Biot-Savart's law in the 50s and what is used nowadays, terms have been removed for simplicity. And if you want to get it back to the physics, to this port Hamiltonian framework, you have to go back a little bit to the original formulation in order to see whether the terms have been dropped or not in a way that preserves the structure. And every time we've tried it, we could find it. So actually in the Euler equations, there's also two terms which are usually dropped. And we had to bring them back in so that when you drop them, you have to drop them in a symmetric way or skew-symmetric way. But that is usually not so difficult. You just go back to the original physical modeling, and then you do the asymptotic analysis or the model simplification on that level.
Thanks for this clarification. Alfio, there is a question. Hey, Alfio, please.
Volker, just have a couple of questions. One is about this, say, tangential interpolation approach, and not sure I understood precisely the goal. I mean, is it similar to what we need just to reduce also the nonlinear part of the problem?
Yeah.
Like
so
the one that you go with this, say, discrete interpolation, discrete implicant interpolation.
Yeah.
Is it
so?
Goal?
You want to do Galerkin projection in some way, and now how do you construct the projection space. The projection space is usually the hardest part. I mean, in proper orthogonal decomposition, you generate it from snapshots. If you have parametric models, you generate it from sampling, or if you have reduced basis, you use simpler models. And that's what we do here. The tangential interpolation approach is the main aspect here is you can use it in models that are generated just from input-output data. So you generate a model from input-output data, then you do this tangential interpolation, and you can do that in a Port Hamiltonian way. That's rather recent work by Peter Benner and Paul Van Door and the people from that crowd. That's why tangential interpolation came into the game again. Before that, it was mainly POD and reduced basis method. But the parts that are generated from data, so-called realizations, there it's really fantastic.
So it's a way to generate the subspace by simply considering the input-output function.
Considering the input-output function as a transfer function, a rational function, and then doing rational interpolation using this tangential method. So
then you can also regard it as a method to generate subspaces on a purely data-driven model.
Exactly. That's what the basis, why I mentioned this here.
Oh, I see. Now, my second question is just to make sure that I understood. Well, you at a given point, you talked about the way you treat the boundaries.
Yeah.
And I'm just wondering if boundaries mean in this case the junctions between different pipelines, for instance, or different pipes. Is that correct?
That is one part of the boundary.
Okay. So just stick with this, please.
Yeah.
Then, if say at a boundary in your system of network of pipes, say, if a boundary is indeed a compressor station that I presume you model in terms of very complex systems of order differential equations, when you have, different type of laws that you want to enforce there.
Yeah.
Is it easy to put the whole thing, the whole model into a way which, if I'm not wrong, was linear, that you need to have your Port Hamiltonian system guaranteed?
No, the whole model can be nonlinear as I described it in a way, but the compressor station, honestly, we have no way to model it in a reasonable way. So essentially that we treat as a black box with input-output data.
I see.
And for example, in this realistic from industry, we have years of data in 3-minute intervals. So we have a time series of pressures and velocities in 3-minute intervals. And there's no way that you describe what's inside the compressor station. So this is a data-based model, and we use a linear model there.
Okay.
I mean, there is a nonlinear model behind, but
sure,
we have no clue how to describe it in a reasonable way. On the other hand, I must say, that's why I mentioned it at the end here in this part here, data-based realization. It's not perfect yet, I must say. The input-output data realization by these linear models, it's very sensitive. The models that come out there are highly ill-conditioned, and so we're working on this, but it's not solved. We can do a Port Hamiltonian model purely from data. That is nice, and that we can stick to all the other models in a network. But I would say there's a lot more work to do here to do this in a way that is numerically sound. even with this paper by Peter and
Van Doren.
Paul Van Doren, I think if you have many data and a long time period, what we get out there is not good. And that would also be the same for almost every other model where you have a black box data structure inside that you generate completely from data. If you don't have the physics behind it, it will come out to be, even though we know that this should be a port Hamiltonian system. But for example, the energy that is used in the compressor station, that is usually completely ignored in the gas transport. But that would destroy the dissipation inequality.
Sure, absolutely. Yeah, I have no control on that.
Yeah, it's no control over it. And the companies say, okay, that energy is not much. But if you have to pump the gas from Russia to Germany, that it's not negligible.
Negligible, yeah.
Yeah.
Yeah, clear. Thank you.
Are there other questions or comments? Luca, please, Luca.
Just a curiosity, have you ever used your model for gas flow, also for leakage detection? That I know it's a big problem in pipe industry, in pipe network, where you have to localize a place where you have a leakage.
We have not done that, but our industrial partner is very much interested in that. At the moment, they are essentially look at the pressure differences, and they have sensors every 30 kilometers or so in the lines. And if they detect that the dissipation is bigger than and the leakage, there is some potential leakage, then they send a person out there.
Okay.
So, but this would be a very good example, and that's exactly what we need digital twins for.
Yeah, thank you.
Other questions for Volker? I have just last maybe or curiosity about this slide, precisely these slides, just to have an overview, which there are some specific, let's say, structure of this model that make the stability or error estimates or precondition in what you have written here about the discretization difficult, in the sense that will be they characterized by technical issues, let's say, or there are some specific trick or issues that should be addressed when one wants to discretize. I saw that you have already used a ROM, so reduced basis, so it seems that all could be applied quite easily.
Actually, one of the motivations for us to do port Hamiltonian model is if you use just Galerkin projection in ROM and reduced order modeling, you would get the same port Hamiltonian structure, and that automatically gives you a Lyapunov function, which allows you to analyze the stability much more easily than in an unstructured model.
Yeah.
And when we have done it for a combustion engine, the reduced models were always unstable. When we rewrote them in a port Hamiltonian framework and used Galerkin projection, we get the stability for free.
Okay.
The error estimate is a harder problem, because in space, if you do mixed Galerkin, mixed finite elements, for example, the reduced system is again port Hamiltonian. The problem that you have is that the usual estimates use some concatenation of nice inequalities that we have in function analysis, Young and Hölder and so on, and triangle inequality, and these usually don't reflect the structure. So you would have to do these estimates newly. That's why I wrote this down here. On the other hand, this should not be such a big deal to do it. It's just technical to do it. Actually, I've thought a lot whether I should look at your the Alfeus models where you combine the electrical for the small veins and the fluid dynamics for the big veins, where at the link between the two, I can use this structure in a nice way so that you get automatically nice reduced order models. I'm truly convinced that this will work very nicely, and that you can get to lower orders, much lower orders. Because at least in the linear case, what we have shown is that the distances to instability or non-passivity and the error estimates are much, much better. So the distance to instability after projection is much bigger than in non-structured.
Okay.
So this is my hope. On the other hand, if you have a bifurcation, we've also looked at bifurcations, and the bifurcations, the places where they bifurcate will change. And so because of the projection. And so we haven't analyzed that. But there are quite a lot of people working on this in different domains. And I must say, what I'm pretty happy about is many communities now switch to this modeling because you stay so close to physics. So the power systems guys are all switching now. And that's a good sign. And also the pipe flow for district heating and things like that. And we've even done the Italian power network to synchronize it with this, and it was much better.
Okay, very, very good. I would like to ask to the audience if there are other questions for Volker. I don't see other comments, so I would like to thank again Volker for this seminar, and I hope to see him soon in some conference or even at MOX. Thank you again.
Yeah, thank you. Bye-bye.
Bye, Volker.